Okay. So yes, it is my pleasure today to introduce Ruowang Li. He's an assistant professor of computational biomedicine at Cedars-Sinai, so just down the road here. And his research integrates machine learning, human genetics, electronic health records, multi-omics, and is mainly focused on the development of computational methods, really integrating all of that, I think, in the big picture of things, for computational methods to understand complex disease. He did his work at sort of training at UPenn with Jason Moore, who's leading up the Cedars-Sinai group now there and expanding that. And so today he's going to talk about the genomic discovery and predictive modeling with Biobank-Linked EHR data. So thank you very much.
Thank you. Yeah. Thank you for the introduction. And thanks to Eric and Dave for inviting me to give this presentation. So I met Eric at GSM this year. I also met with April. I think she's from Genetic Epi. Yeah. Also this year at ASCG. Yeah. So I'm kind of meeting USC faculty in the wild starting this year. So 2 this year, so maybe more in the future. So yeah, so I'm going to talk about some of the kind of ongoing research and past research in my lab. So little background. Okay. So yeah, so before I was at Penn, shoveling snows at this time, maybe around this time. So I moved to Cedars a couple years ago. I really enjoyed the Southern California weather. So my research, is kind of at the integration of genetic EHR and omics. So as a kind of junior faculty who work in this very established field and very competitive fields, so my lab is really trying to come up with kind of innovative ideas borrowed from this computational field and apply them and adapt them to the genetic research. So that's kind of the focus of our lab. And so I want to start with something I think we can all agree on. We need more data. So increasingly, data is driven discovery in biomedical research. And the data are like pulses. We have our systems. So we have omics research, there are more molecular data, genomics, epigenomics, proteomics. We also have clinical data, measures the kind of clinical history of the patient. We also have imaging data that's more focused on different organs and different disease. And we also have disease-specific data that are really measuring the unique characteristics of different diseases. So, why do I, although all these different data, why do I work on the EHR data? So I will give you some of the kind of unique advantages of this data and maybe convince you this is a good data to use for research. So first, EHR data, we go to a hospital, we collect information, we have structured data that measures the kind of lab tests, the diagnosis, and all the clinical history. We also have unstructured data like the clinical notes that are being increasingly mined by like NLP or large language models. And so we have this data, and typically this data is really large. So we have EHR data is a large real-world patient population, and it's not uncommon to have EHR data have millions or tens of millions of patients if you work with a large hospital. So it's very large and real-world patients data. And secondly, EHR data captures a lot of things. So it's not a disease-specific data set, it's disease agnostic. It captures a rich clinical detail across diverse conditions. So you can use EHR data to study many different conditions, and you have many different variables already collected for those conditions. So it's a very rich data for many different applications and method development. And third, as someone who just started a lab, cost is very important. EHR data is very cost effective. So I don't need to collect the data. The data is already there. So there is some data access fees for some EHR data, but it's still very much cheaper than collecting my own data from scratch, right? Compared to this molecular data or imaging data. You really have to recruit the sample, pay for all the tests. So it's very expensive, but EHR data, because it's not designed for research, it's just been collected all the time. And we just need to process the data, make sure the data is of high quality, then we can use that for research. So it's generally almost free. And lastly, I think it's increasingly prevalent now is EHR data are now being linked with other modalities. So in my talk, I'm going to talk about linking EHR data with genetic data, but I'm going to mention a couple other examples. So EHR data are going to be, you can also link imaging data and other molecular data with EHR. So you basically have this very huge clinical data that's very rich, and you start linking with other modalities. So you can look for correlations among the clinical clinical outcomes with all the other modalities. So I think these are, of course, there are biases and other considerations in the EHR, but to me, this is a really good data set to use for developing methods. And so in my talk, I'm going to talk about a special EHR data. So a lot of institutions have biobank linked with EHR. So you collect patient samples and you store the patient samples there, and most of the time it's unused. But starting more recently, a lot of biobanks are starting to generate genetic data from the blood samples. So from these patients, you do sequencing or genotyping, and you have genetic data for these patients, and you can link the genetic data with the EHR data. And the kind of unique advantage of this is you only need to sequencing once for the whole patients, because the genetic doesn't change across a person's lifetime. So once you have the data there, you can do all sorts of kind of interesting things connecting with the EHR. So one-time generation, and you can do many research using the EHR data. And so this is an example. This is a paper published last year. So if you look across the globe, there are a lot of increasing number of biobank-linked EHR that are being used for research. So the most earliest one and the largest one is the UK Biobank that has been established for, I think, over 10 years now. And the kind of US equivalent is the OAFAS data. It's recruiting a more diverse population, linking the EHR with genetics. But we also have EHR biobank-linked EHR in Europe, in Asian countries. And since this published last year, this figure is already outdated. It's just this year, there are more kind of biobank-linked EHR being kind of published and being used for this type of research. So this is an ongoing and kind of increasing resource in this field. Just to show you an example, the scale of the data. So these are some of the example biobank-linked EHR. You can see the sample sizes are like huge compared to more molecular data, more like imaging data. So hundreds of thousands of individuals. Some of the data have over 1 million individuals. Right? So most of these biobank-linked EHR have linked genetic data. So that's one of the most common linkage is to link genetic data with bio EHR. But some other biobank EHRs are starting to link RNA sequencing data, proteomics data, and COVID data. And it's not mentioned here, so some EHR also have linked imaging data, metabolomics data. So all these data are linked to their clinical records. So we can do very interesting things with this linkage, data linkage. So today I'm going to talk about 3 different projects, and we developed methods to analyze or use this biobank-linked EHR data. You might be a little ambitious to talk all 3, so if you don't have time, you can just talk 2. But if I have time, I want to go through all 3. So my idea is to more like give you an iteration behind the method development to showcase like the power of the data, and to give you enough information, you can tell me whether it's a good idea or a bad idea. So that's my goal today. So first, I want to talk about a method we developed that's for the federated learning integration of multiple EHRs to study genetic pleiotropy. So just to start, give you a background on what is genetic pleiotropy. So in the most simplest term, genetic pleiotropy is if we have a single gene or a single genetic loci that are correlated with multiple outcomes. So that's a quite simple definition. And the correlation doesn't mean causation. So we are not looking for causation here, but it just means potentially a single locus in our genome is affecting multiple disease trajectory or disease onset. So that's what we want to find. Okay. And this figure, if you are not familiar with the genetics, you might be wondering what is this kind of mess here. So this is taken from the GWAS catalog. So each of this kind of sequence is a chromosome in our genome, and each dot is a unique genetic association between one single SNP and one single outcome. So each dot is association. So I think this figure has probably tens of thousands of dots now. So we have many GWAS associations that associate with a single genetic loci with a single disease. But if we start to plot this on a genome level, we can see many of these dots stack on top of each other, right? So that means the single genetic loci has been found to be associated with different disease traits. So why do we study pleiotropy? First is widespread across the genome. So we see this a lot across the genome. And what can we use this information for? So first we can use pleiotropy to review the shared genetic mechanism across traits. So if we see two traits and we look at the overlaps of the genetic associations, and if they are similar or not similar, we can tell us something about the underlying genetics between the different disease and traits. And secondly, we can use this information to improve the interpretation of the association. So most of the GWAS associations, we don't know anything about the loci. We know they are associated with the outcome, but we don't know anything else about the actual genetic associations. So if we know the same SNP is associated with multiple traits, it helps us better understand what the actual, like the same or genetic loci is doing, right? And thirdly, it's more clinical translation. We can use this information to develop for drug repurposing. So if you have a drug that targets a condition and the condition have a certain genetic factors associated with the condition, and if we know another condition that share the similar genetic factors, we can potentially repurpose the same drug to treat other conditions, right? And lastly, we can also use this information to develop genetic risk prediction models. So we develop a model for one condition. If two different conditions share a similar genetic factors, we can use that model to also apply to other conditions. So these are some of the use we can use for pleiotropy. And quite a simplified view in the biobank data. So you can imagine in the biobank, we have each row is a patient. We have different conditions measured for each patient. So a patient could have multiple different conditions. And on the right-hand side, we have a genetic data also matched with the patients, and the SNPs are like features in the genetic data. So how do we find these pleiotropy associations? So quite simply, we look for each individual SNP across all the conditions. So that's how we generally do it, and we do it one SNP at a time. That's how we test pleiotropy. And the most common method to test for this kind of association is called PHAS. It's called phenome-wide association study. And what this does is we simply summarize individual GWAS associations. So in GWAS, we test each individual loci with one condition, right? We have this result from GWAS, we stack them on top of each other. We find the common kind of significant association across the same loci. So that's how we perform the PHAS analysis, and that's how we kind of identify pleiotropy. And there are a couple of issues with this analysis. First is the computational time, because we have to look for all pairwise comparisons, and also with the increased multiple testing, because if we start to increase the number of traits we test, we are doing so much more tests, right? And there has been already methods that are designed to kind of address some of these questions. But what we want to hear is, can we do better than existing methods? And the angle kind of innovation we are trying to incorporate to this is, can we integrate multiple EHR data to look for pleiotropy analysis, right? So as I mentioned before, we have these large EHR data across multiple institutions, across multiple continents. So we want to integrate all these data to do a more powerful test, right? By integrating different data, we obviously increase the sample size and reduce the power, and you can also increase the generalizability of our results, because each EHR may be focused on one region, so it has some characteristics from that one region. By integrating data from like different regions, we can average out these kind of noise, and hopefully we can give us better time to find signals. But on the other hand, it's very difficult to integrate EHR data because of privacy protection and also the communication cost. When we want to integrate data, we don't want to share the data many times, and in most cases, we can't even share the data to do the integration analysis.
So the increased statistical power here, isn't that just focused on each individual GWAS? You have increased power to detect loci, or is there something about the biobank, the biobank EHR usage that improves power for the EWAS component of it?
Yes, yeah, mostly it's just increase sample. We stack them together, it increases sample size. We have more people in our data, but instead of using one EHR at a time, we kind of combine them all together to do a kind of unified integrated analysis. Right? But the method we are trying to propose is how do we more efficiently integrate this data together without sharing the raw data. Just to give you some of the challenges in kind of integrating this data, so the most common data we use is the UK Biobank data and the OAPAS data. So all these data are synced in their respective cloud. So before we can still download UK Biobank data, but now we can no longer download data. So they all sit on their cloud, they have their own systems, you can't download any data. So that means we can't just download the data, combine them into a larger data set and do analysis, right? So we need to develop methods that can kind of integrate this data without downloading data. So that's kind of our logic behind developing this method. And so there are already some existing methods that does this. So in the gold standard approach, which is the ideal case, if we can just combine individual level data, that would be the best. Right? We don't lose any information, and we only do it one time. So it's lossless and non-iterative. So just to, so normally there's a trade-off between the losslessness and iterativeness. If you want the data integration to be more precise, we generally have to transfer information multiple times. And if we want to reduce the transfer of information, generally we lose some information. So that's kind of a trade-off in this kind of data integration methods. And some other methods like in linear regression, we can get exactly the same kind of integration without losing any information. But for some other methods, we have this trade-off, whether we lose some information when we integrate, or we have to transfer information many, many times. So this is talking about not transferring raw data, but transferring summary statistics across different data sets, right? So our kind of idea is to develop a method that does a lossless integration, and also we do want to transfer the information many times. And we call this SumShare, and this is a joint work with our collaborators, Ruowang, Ying Chen, and Jason Moore. We call it SumShare. So the key idea is we want to do this kind of integration across multiple EHRs, and we use a composite likelihood. So first to decompose the likely function across different EHRs and different patients and different phenotypes. And within each of these kind of combinations, we use a score test to kind of decompose the test statistics into different components, right? So you can see the score test only uses kind of summary level information within each of these combinations. So it uses the mean of the y, so that prevalence, use some combination of the x and y's to decompose this score test into this. So through some mathematical iteration, we can show that it is exactly the same as if you do an integrated test when you combine the individual level data, right? So that's kind of the key idea behind this. So here I just want to show you only require one round of communication. So what the SumShare does in each site, in each EHR, we calculate a summary statistics. They include like the prevalence of the data, the variance of our SNPs, and some of the covariance between the SNPs and the outcome. And we transfer this information to a central analyst, which calculates an average statistics, and we use this average statistics to conduct a score test. And the first thing we want to show is the SumShare produce the same result compared to pooled individual analysis, because we claim it's a lossless analysis. So in this case, we randomly put some subset of SNPs, and we conducted a kind of multi-outcome association. And on the y-axis, on the x-axis, we show the p-value when we conduct a pooled individual level data analysis. That's the p-value. And on the y-axis is our analysis only using summary data. And as you can see, we basically achieve the identical p-value between these two. So that means we are not losing any information by only using the summary statistics. So next, we also show that some share has higher power than PWAS, so across different simulations. So as you can imagine, pleiotropy, some of the SNPs could be associated with many diseases. Some of the SNPs may be only associated with a subset of disease, and some SNPs may be associated with no disease, right? We consider all these different scenarios to design our simulation, and we can see that we have better power compared to the kind of more common approach PWAS. And if you notice closely, we only see 3 curves, but we have 4 different methods. So this is to show that actually our method, whether we pull the data or use summary data, it gave us identical power curve. So that's another indication we are not losing any power when we only use the summary statistic. And we applied this method to across 8 different EHRs in the US through the eMERGE network. So through the eMERGE network, we have access to 8 different EHRs, and we look for pleiotropy association across 5 different cardiovascular related disease. And this shows you there's a kind of huge differences in terms of sample size across different diseases. So the main result I want to show here is if you just perform the analysis on individual EHR data, and because of their limited sample size, we don't see very few or just one association if you just focus on one EHR. Right? This is if you combine the 2 largest EHR together, and we see an increased number of significant associations. And finally, if we combine all EHR together, we see a larger sample size and we see a lot more significant association. That shows the power of integrating across all these different data. Right? So the sum share is kind of limited to only binary outcome, but in reality, we have mixed outcomes, both binary and continuous outcome in EHR. Also, we may have more heterogeneous distributions across different EHRs. So we have different age distribution, different covariance distributions across different EHRs. So we extend the sum share to a newer method called mixed WAS. So the mixed WAS basically have a better generalizability. It can account for both binary and continuous outcomes. It can also adjust the differential covariance distributions, and we apply this to kind of more traits as well, cardiovascular traits, both binary and continuous, and we also apply to the same eMERGE data. And similarly, we see a kind of big increase in terms of significant associations, and when we take what we found from the eMERGE and we validate it in the UK Biobank, and we see many of these associations also validated in an independent cohort. So it not only increase power, it also increase the generalizability of our association. Okay, so that's the first project is to show you the kind of power of. Okay.
I'm sorry, I didn't mean to.
Yeah.
I guess maybe I'm trying to get the multivariate part of this in there because I think I might have missed it in your equation, but it looked like you were just summing up over kind of the EHRs, the phenotypes, the SNP.
Yeah. You assume they are
You're
independent.
incorporating the correlation of the SNP somehow, right, to get conditional type of estimates?
Oh, I see. That's a cool
like,
question. Yeah.
I'm thinking in the sort of the traditional use of summary statistics, right? You have a reference data set. Here you could get the entire reference, data set from the EHR in terms of the correlation matrix. Is something like that used behind the scene for that side, or is it also the phenotype side that's multivariate correlation?
Yeah. Actually, it's not using any correlations in either side. So it's scanning one step at a time.
It's still independent in all that.
Right? Okay. So the power of this is it gives a more like hypothesis generation. So it's still doing one step at a time, but it scans across multiple traits at the same time. So once you take this, you have a smaller candidate set. You can do more kind of sophisticated defined mapping or doing kind of conditional analysis for the subsequent steps, right? So this gives you a faster way to kind of scan across, across many traits.
Got it. Okay.
Right.
I have a follow-up question.
Sure.
Just two questions. So when you showed the something like 1,700 SNPs you saw associated at the top of that one table, that's a lot of those are probably in LD with each other.
No, yeah. There are some. Yeah, there are definitely some in LD because we are scanning them independently. There are some in LD.
That makes sense. And then I guess the other thing, you may have said it, I might have missed it, but what is the basic test that you're doing for a fee loss?
basic test, I think in the most basic term is just a logistic regression controlling for some cohorts. And if you want to integrate FIWAS across multiple sites, you just do a meta-analysis across multiple. So that's what we compare to. When we compare our test with FIWAS, we use the meta-analysis for apply to the FIWAS, and to combine the p-value. Right? We have different ways to combine p-value. We tried multiple different ways. Some of them is more. Let's see, what was it? We tried the most basic, like Fisher's method to combine p-values. We also tried more recent development, ATAC, some sort of p-value combination. I didn't do this part, so I kind of forget. But
so if you, let's say you had 3 traits and you had a 10 to the minus 4 p-value for each of them, so none of them is significant by themselves.
Yeah.
But then you do meta-analysis and it pushes it to something beyond 10 to the minus 8, then you would say there's pleiotropy?
So when we do the FIWAS, we have one SNP, across different traits. Then the first thing is across different data. So for that each individual trait, we first do the meta-analysis. Okay. So for that trait, we meta-analyze across different data sets. So then we have, if we say 10 traits, we have 10 different p-values. Then one way is to just look at the minimum p-value across these 10 numbers, right? If there's a minimum that passes the whatever threshold, then we say there is a potential pleiotropy. And another way is we combine the p-value in a certain way. We consider correlations, maybe among the traits, we combine the p-value, then we use that p-value to make a determination whether it's significant or not. So it's one or more. So most of these analysis doesn't distinguish whether it's 1 or 2 or 3. It just means there's at least 1. So that's why you need a subsequent kind of analysis to see whether it's actually 1 or 2. So in our paper, we actually look at the distribution of the p-value. So we take the significant kind of SNPs and we perform a separate test for each individual trait, and we look at whether it's actually one SNP significant, or 1 trait, or 2 traits, or 3 traits. Most of them show around 3 to 4 among the 12. So there are some kind of potential pleiotropy effects there. So it's not just driven by kind of one single phenotype, even though it can be. Okay. All right. So I'm gonna kind of switch gears to talk about another application using this kind of EHR data. Is about developing a kind of better polygenic risk score. So give a very kind of brief summary of what a polygenic risk score is. We still go from the GWAS. We take this association for the disease, but instead of looking at one SNP at a time, we combine all the association into this one score. So we do a weighted average of each SNP and combine them into a single score. And once we have the single score, we can see, okay, so these individuals have high genetic risk based on this combined score across the entire genome, and these individuals have lower risk score. So we have this distribution, we can start to do risk stratification, we can start to make predictions. So that's in the most simplest form that what the polygenic risk score is. And we, along with other people, have shown that we can use EHR data to develop polygenic score, which is I think pretty obvious because we have EHR data, we have many phenotypes, we have genetic data, we can develop using the same EHR data to develop thousands of different polygenic scores across many traits, right? And people have done that. So we ran all pairwise polygenic score for all the traits in the EHR. And one challenge is when you start with this very interesting problem, there are many different methods. So many different methods are trying to address the same question. And across many different data sets. So if you use a different data to develop the same polygenic score for the same trait, you may end up with different kind of risk scores because it depends on the original GWAS association. So there's a lot of variabilities in terms of methods and the data that are being used to develop PRSs. And many papers have shown that no single PRS performed the best across all diseases and traits. So in some data sets, one method may be better. In some traits, another method may be better. So there's no uniform best methods right now in terms of developing PRSs. And another kind of opportunity is we have these centralized databases I'm showing here is the PGS catalog. It kind of curates almost all the existing PRS that has already been developed. So you can see there's already 4,700 PRSs across hundreds of traits, across hundreds of publications, and this resource is growing. So we have more data available, so more PRS will be available, more methods, more kind of models are available on these centralized databases. So our idea is, so instead of building another PRS from scratch, which is very hard to do, to build another model that outperforms all existing model. So why don't we take the pre-trained fine-tuning approach that very common in like large language model, right? We use pre-trained model, we fine-tune them to make it better. So we use that idea in genetics. So what we do here is we take this existing PRS as a pre-trained model and we apply some fine-tuning. And hopefully through fine-tuning, we can find potential missed signals that are not captured by existing model or misspecified models. So not all the models have correct assumptions or just data variation. So the data, the PRS generated from the external data may not be similar to your target data, right? So there may be some missed signals. So through fine-tuning, we want to add these signals back to the pre-train. So pre-train may already give us like 80% there. So through fine-tuning, we want to find the remaining 20% of the signal. So the kind of final product is the ABPRS. We want to adapt the fine-tuning the pre-train model to give us a better PRS. And so just to give you like a summary of like an overview of the steps. So the first step is, on the left-hand side, these are the potential signals that we want to capture in the PRS. So the PRS mostly capture the first type of signal, it's the additive signal from the GWAS. So GWAS is the model under the additive assumptions, so one of the assumptions under GWAS, but there are other type of signals that are not being efficiently captured. One is additive uncaptured. So even though the signal is additive, maybe the GWAS didn't capture the signal because of power issue, but there are also other types of genetic signals like dominant, recessive, and other types of signals that are potentially missed by the pre-trained PRS, right? So our first step is very simple. We use the pre-trained PRS as our baseline, and we scan through across the genome, and we look for the remaining signals that are not captured by the pre-train. So it's kind of finding the orthogonal signals that are not captured by the pre-train. So we scanned through all this, and we came up with a new data encoding. So for each of the SNP, we take the residual signals and convert that into a new coding for each SNP. So now the SNPs only code the remaining uncaptured signals. So that's the first step. Do a genome-wide scanning to see what are the potential signals that are remaining. And the second step is once we have the signals, a lot of them are going to be noise, right? So we have to find the needle in the haystack. So how do we find the signals from the true noise? So in this case, we have kind of two kind of innovations we brought into this method. So first is we use something called mirror statistics. So in this case, we first divide the data into a kind of training set and validation set. We scan the genome-wide scanning on both data sets, and we look for each kind of SNPs and their signals. So if there's no signals, we expect the signal to be all over the place, right? Central around zero, and some of the signals will be positive direction, some will be negative direction. So they will be kind of random signals, right? But the true signals between the two data sets will share the similar strength and similar directions. So that's one criteria we use to say something is more likely to be true, right? We use a mirror statistic, which gave us a tool set to set FDR threshold to kind of separate the signals from noise using the training and validation data set, right? But another issue is if we keep reusing the same validation data, eventually we're going to overfit on the validation data, right? Normally we can only use validation data once. So how do we keep reusing the same validation data? So in this case, we use another kind of innovation, it's called reusable holdout. So this is a method proposed almost 10 years ago. So what this does is every time we do a comparison between the training and validation, we add a small amount of noise to the validation data. So validation will be very similar to the original validation, but it's not exactly identical. So that allows us to reuse the validation data many, many times. Under some kind of conditions, we can reuse it like so many times. So by using this reusable holdout, so first we can do the scanning use the mirror statistics, and use reusable holdout to reuse the validation data many, many times. And we use this to kind of separate the noise from the signal. And so this is kind of what the second step is doing. So we have a candidate set of kind of signal sigma theta stamps. That's what we call the theta stamps that capture potential uncaptured signals. And we reiterate this step using mirror statistics and this reusable holdout threshold to find the potential kind of more interesting signals and through this scanning. So that's our fine-tuning step. And the last step is very simple. We just add the pre-trained model along with our fine-tuned signals. That will be our final kind of risk model. So that combines both the kind of pretty good pre-trained model and the identified fine-tuned signals. And we apply this to, we did pretty thorough comparison. So in this case, we apply this to 8 different diseases and traits, a mix of binary and continuous. And we also use 3 different sources of pre-trained. So some of the pre-trained we got from this database from PGS catalog. We also got pre-trained PRS from FinGen, which is another kind of large-scale biobank in Finland. We also obtained PRS from a large consortium. So this is a large GWAS consortium that can have 1 million or hundreds of individuals. So we use different sources of pre-trained PRS and fine-tune them all on the UK Biobank. And we evaluate our model across 4 different EHRs. So for UK Biobank, we use a subset of testing data. We also use all of us, eMERGE, and Penn Medicine Biobank for independent evaluations. So if you look across all the method performance, most of the fine-tune have equal or better performance compared to pre-train. So we can show that pre-train actually worked and the model generalized across different kind of independent data, even though we only fine-tune on the UK Biobank data itself. So, I mean, imagine if you fine-tune on multiple data, I think the result would be even more generalizable. So I think that's our goal here, is to find something that's equal or better. So our baseline will be the pre-train. And if we can find something more interesting, we add them to the pre-train model. And we also look at the kind of signals of the fine-tuned signals. So we look at whether there are some interesting patterns. So here we are plotting across, like these show like different diseases, and we did a clustering analysis of the different fine-tuned signals, and we can see there are some interesting signals we find in the fine-tuning. So as I mentioned before, GWAS mostly assumes an additive coding. So it assumes a linear line. So if you see a linear line, that's the additive coding. And we see a lot of fine-tuned signals don't show that kind of linear relationship. So that's not being captured by the pre-trained PRS. So this is a clustering, it's not a quantitative analysis, but it's kind of interesting to see there are so many different patterns in our data. And lastly, we also look at the kind of risk stratification. So in this case, we take the kind of high-risk individual and the low-risk individual, compare the risk stratification based on our model compared to the pre-trained model. And we see in most cases, we see a higher kind of odds ratio of enrichment for the high-risk group and low-risk group. And this has more direct clinical translation, because PRS mostly generally don't care about the middle population and more cares about the higher risk population, because we have more kind of clinical actions for that risk type of individual. So we do see it's more enriched for those group enriched, but not everything improves. So we're not claiming it's always better, but in most cases it's better than the pre-train. Okay, see the time. Okay, still have time. Okay, so that's the talk on the PRS. We use the pre-train fine-tuning approach to use the EHR data to develop better PRS. So lastly, I want to talk about a kind of also completely different approach, is to how to perform variable selection, better perform variable selection. So we have these large data sets, we have more features than samples, and generally we require some sort of variable selection before we do the analysis, even though if some models can handle more features than samples, but it's still computationally very costly to just throw the data in there and see whatever we get, right? It's generally better to perform some sort of variable selection before we perform the analysis. And I will argue that most of variable selections, at least in genetics, use the p-value. So in this GWAS example, we set a p-value threshold. Anything above this threshold we consider to be important. Anything below, we don't really kind of look at them anymore. And so the next question is, if we want to take this significant SNPs, generally we want to do some downstream tasks, right? We take this significant SNPs, we want to do something with it, and sometimes we want to do predictive modeling. We want to use the SNPs to see whether we can use this information to develop a predictive model or to predict some treatment response. But the question is, are significant variables good predictors? Right? That's a question to ask. Are they one-to-one? And I want to show you this paper. I think from the title you can see they argue that significant predictors aren't automatically good. Significant variables aren't automatically good predictors. So it's not exactly like something significant, it has good clinical predictive value. Right? And so these are kind of some of the questions we want to address. So first is, are there better alternatives than significant-based selection, variable selection? Is there a question? No, okay, just use it, okay. And if there are there different methods? Do different methods select the similar variables or different variables, right? That's the second question. The third question is, can we unify different variable selection kind of approaches? And the last question is, can we improve our performance compared to just significance, right? I think these are all important questions. Any one of them didn't work, and then we are now proposing a good method. So just give you a kind of intuition. So here I'm showing you kind of typical way to do variable selection. We have a number of features, and we do get a p-value for each of the feature. We have a cutoff. Anything above the cutoff we consider to be important. But if you're familiar with like video games, right, we have characters, and each characters have different strength. And I think that's also what applies here. So each features may have different strength under different selection criteria. So some features may have really high AUC, but low precision, right? Some other features may have really high p-values, but they have low AUC. So if you only look at the significance that only represent one dimension kind of characteristic of the feature, and we are kind of missing all these other informations, right? So our kind of idea is can we combine the strength of different feature selections, give us a more uniform feature selection criteria. Okay, so that's the motivation. So we propose a method called mixer. Some of the key features is first we want to leverage different selection criteria, including p-value, AUC, and other these more predictive feature selections. And second is we want to do a more quantitative selection, not just qualitative. We don't want to say, I'll take the top SNPs across all and merge them. So we want to have a more quantitative way to combine them. And the third is when we integrate them, we want to have these adaptive weights that are based on the data, not just based on kind of expert opinions. So yeah, similarly, I want to just give you the intuition without going to so much math. So first, what we do is under different variable selection, we first perform variable selection under different criteria. So we select features under p-value, accuracy, balance accuracy, etc. So we have a sense of how each variable perform under different selection, right? Then we can look at them together, right? So once we have different variable selections, we can also evaluate the different variable selections under different evaluation matrix. So we can see whether a p-value, how does the p-value selected features perform under accuracy, under AUC, under precision, under F1. So we can have this pairwise kind of all combination of comparisons. So now with this comparison, we have an idea of how each selection performs across different evaluation criteria. Right? It gives us a sense of the kind of robustness of variable selection and the performance of variable selection under the kind of distinct criteria. Then we can start to quantify this kind of performance. So we can we come up with a predictive importance matrix, basically quantify this relationship across different selections and different evaluations into something more quantitative that kind of normalize the performance across different matrices and different evaluation criteria. Right? And the second step is we want to integrate this quantification with their individual selection. So under each individual selection, we also know which features is more important, right? So the intuition behind this is if a selection is very good and we give more weights to the features that are selected under that particular selection, right? But if a selection criteria is kind of poor or bad, we give less weight to the features that are selected under that particular selection. So we start to quantify the combination of kind of feature selection matrix as well as the features that are being selected under that matrix. So we combine them together, and we use a kind of easy tool called adaptive lasso. Basically, come up with the new weights that combine these two information, and basically we have a new weights that prioritize each feature that combines their information on their selection, right? So I'm just going to show you one result. I hope this result convinces you this is important. So we look at the top SNPs selected by different criteria for Alzheimer's disease in UK Biobank. So here I'm showing you is, okay, so first is each column, each row is a different selection criteria, and the first column show you the selected features p-value. So the first row is if we select the top 1% of p-value, of course, the p-value will be very significant, so we see a bar in the top 1%. And the second kind of column is the MAF distribution. So this tell you about the variance of the features. So if you select by p-value, you're selecting kind of more kind of rare SNPs in general. And the effect size distribution, of course, we see there's a gap between around 0 because we are selecting a significant p-value. So we expect the effect size to be non-zero, right? But if you start to look at across different other selections, we see a very distinct patterns. Like if you just take AUC as an example, so some of the AUC, high AUC SNPs, also show a significant p-value. So this is consistent with p-value, but AUC also select all of these other SNPs that have really low to like almost insignificant p-value. So if you only use the p-value to select, you're going to miss all of these SNPs here, right? And we see across different selections, they are really selecting very different things, right? AUC and balance accuracy have like a similar distribution, so they are kind of selecting similar SNPs. But if you look at F1 score, precision recall, and they are really selecting completely different things. And our goal is to kind of grab important information from other metrics and combine them with the p-value, and hopefully we are selecting a more robust feature selection. So I'm not showing you the result, but the result, of course, is better. The proposed method is always better than existing methods, but we do show it's working well for UK Biobank. We also validate the model on ADSP, which is the Alzheimer's specific data. It also shows improved performance. So, oh, perfect. Okay. So in summary, I hope I can convince you Biobank-Linked EHR is a powerful resource for novel genomic discoveries, and integrating across EHR can improve the power and generalizability of the results. And it also provides a kind of robust development and validation for polygenic risk scores across diverse disease and traits. And finally, I just want to say there's other opportunities remain for advanced methodology development and also multimodal data integration with this kind of data sets. And finally, I want to acknowledge my kind of collaborators and data sets and some of the following scores. And I'll take any questions. Thank you.
Great. Thank you very much. Any questions in the room or online?
Can I ask a question about the last project you run? I think it was like slide 58 or so, and you showed all the different, I was just contemplating those bottom 3 rows, at least in terms of the p-value distribution, they look kind of similar. I guess when you were deciding which of the metrics to include in the index, is there the potential that those are picking sort of similar things? Are you overweighting that kind of concept if those are all kind of similar metrics?
Yeah.
I can't quite read them there, but.
Right, they are because F1 precision recall, they are definitely correlated. F1 is just a ratio of precision recall. So what we do is we basically we use a data-driven approach. They may give similar information, but we evaluate different metrics in the same way. So we take F1 selected features and we look at the performance on F1 precision recall AUC across all the evaluation criteria, and that will give us a sense of how well that feature, that metric is. And so that's kind of one way to incorporate them, give different weights to them. So, but if they do select similar features, I guess they would be resulting in similar weights. But I think I'm not showing here, we also look at the overlap of the features selected. They also I do see them select different things. So they're not completely overlapped. There's still some features that are unique to even F1 precision recall. So now they're not identical. So if you look at the precision recall, you look at the effect size, somehow one is picking up like negative effects, right? One is picking up positive. So in that case, they are definitely not picking the same features, even though in terms of p-value and MAF, they are similar, but their effect size are quite different. So they are picking different features.
I have a question.
Sure.
So regarding your pre-trained PRS section, you were kind of speaking in general terms of how it works, but have you ever looked at sort of a pre-trained PRS that was done mostly on individuals of European ancestry, and then the additional subsequent is on specific populations to see kind of what are the additional SNPs needed to really hone in on that population?
That's a great question. So far we only look at European ancestry for the paper. Actually, I wrote a grant to do exactly that. So take the pre-trained European, fine-tuning on other ancestries, and see if it improves. But of course, there's additional considerations, like the LDs are different between the pre-trained, between the different ancestries. Maybe not the same SNPs map across different ancestries. So there are other considerations. So that's definitely our next step. Hopefully we get funded to do that. That's our hope.
Yeah, we should. We have the multi-ethnic summary statistic for most cancers. We should talk about how you leverage that data. We're happy to hear.
Awesome.
Jose Luis has a question online.
Yeah, so this is like a practical question. So in the motivation for your federated regression algorithm, you have like the all of us and the UK Biobank. Have you been able to convince like either all of us or UK Biobank to let you install your code in their enclaves so that you can actually do the federated thing?
So for the validation, the model is very simple. We only have like pre-trained score. We have a few of the fine-tuned signals. So it would just be a very simple regression analysis, and we just use R. We didn't install any kind of custom software on all of us. It would just be like using their cloud platform. But we do have a lot of trouble using all of us. Just want to share. It's not like a super easy thing.
Yeah, okay. I'll follow up offline. Thank you.
Okay. All right, thank you.
I've done some work on federated learning, and it's kind of hard to convince.
Yeah.
In the second, third, and fourth panels there, rows,
Okay.
it looks like the effect size is centered around 0 for all of those. I can't tell what the scale is on the x-axis, but I'm trying to think of measures like AUC or any of those that would have any impact when you have a 0 effect. So how does that count?
There are some that are close to 0. I think because maybe the bin size is average, but there are some that are kind of small but non-zero. In terms of prediction, why would there be kind of close to 0 effect size and still give you better prediction? And I think maybe it's the kind of binning, because it's kind of maybe binning the smaller effects into like close to 0, because the bin size maybe covered the 0.
So those are sitting on 0.
And that's a good point. So maybe we should change the visualization to
I
leave
just
a
can't
gap.
see the scale, so I wasn't sure if that was on 0 or on something else.
Right, that's a good point, Okay.
Any other questions? Thoughts, comments? Okay. Thank you very much.
Thank you.
Excellent.